Hi everyone, Zas here. In this video, we're going to talk about Wolf's standing net clutch in Virtua Fighter 5 Final Showdown and some of the mathematics behind it. In this video, we're going to try to answer the following questions. What is the best strategy to use? How much damage can you expect to get? Is it better than guaranteed damage, and if so, under what conditions? Okay, so first, let's recap the standing net clutch. The net clutch is a throw stance from which there are three options. Wolf can initiate the net clutch in two ways. He can hit with 4 kg, or he can hit with his raw Real American Wrestling stance. Once he's there, he has three options. He can hit back in PG to deal 65 damage. He can hit toward in PG for 70 damage. And finally, he can hit neutral in PG for 50 damage. To simplify things, at this point, we're just going to assume that Wolf is in the net clutch stance without worrying too much about how he got there. We can go over how he got there and how that affects his damage and overall payoff later in the video. Okay, so let's take a look at Wolf's options once he's in the stance. What does Wolf want to do here? It's not immediately obvious what his best move is. One thing he could do is pick the most damaging move, which is toward. However, if he did that, the opponent could adapt by always breaking toward. So it seems good at first, but the opponent can definitely react to it and learn that again how to defend that strategy, and in the end always take no damage. Another thing Wolf could do is he could try to predict his opponent's reaction. For example, he could think, well, the opponent is definitely going to break forward because that's my most damaging throw, so I'm going to go for back. But the problem with that is that if the opponent is smart, he might know and actually outpredict Wolf. Now, some might say that this guessing and counter-guessing is the core of fighting games, and I wouldn't necessarily disagree. But we can still ask if Wolf can do better. Wolf could also mix up between two of his most damaging throws. That seems like a reasonable candidate. Another thing Wolf could do is he could just pick randomly. Wolf could randomly pick between the three choices. But something about that feels wrong. When the toward dimension, the toward direction does so much more damage than the neutral direction. It feels kind of okay if all three directions did the same damage, but your intuition might tell you that something's wrong when the payoffs are so different for the different choices. So is there a better answer? Fortunately, these kinds of problems were solved by the mathematician John Nash in the 1950s. Nash proved that for a system like this, there's a strategy called a Nash Equilibrium. A Nash Equilibrium is the best strategy that takes into account the other player's actions. Basically, it means that you could tell your opponent what you're going to do, and your opponent couldn't do any action to make things worse off for you. Now, this strategy is generally going to be a weighted random strategy. In other words, it's going to be something along the lines of pick neutral X% of the time, pick toward Y% of the time, and pick back Z% of the time. Going truly random, where you pick equally between all three choices, would be a special case where all the weights are equal. Nash showed that in any game there's always at least one Nash equilibrium, no matter what. Now, I've drawn up this matrix here so that we can review the options in more detail. Once Wolf is in the net clutch, there's a couple ways that it can go, depending on what Wolf does and what his opponent does. I've drawn a chart here to go over the possibilities. There's 9 total things that can happen. I've drawn the damage that Wolf deals in the chart. For example, if Wolf chooses neutral and his opponent chooses back, then Wolf gets 50 points of damage. I've listed P1, P2, and P3 as the respective probabilities of Wolf going back, neutral, and toward. Similarly, Q1, Q2, and Q3 represent the probabilities of the defender going back, neutral, or toward. In game theory terms, this would be an example of what's called a discoordination game. The defender wants to pick the same direction as the attacker. In other words, the defender wants to coordinate picks. The attacker doesn't want to coordinate. The attacker gets damage if he picks a different direction. This is actually quite similar to the game of penalty kicks in soccer, where the goalie and the attacker have to pick simultaneously between left, right, and middle, and the goalie wants to pick the same direction as the kicker, and the kicker wants to pick a different direction than the goalie. In fact, the theory behind this game is very close to that of penalty kicks. Okay, so now that we've gone over these terms, let's figure out how to solve this. First, let's define our terms. P1 is going to be the probability that Wolf goes in the back direction. P2 will be the chance that he picks neutral, and P3 is going to be the chance that he goes toward. E is going to be how much damage you get on average. A Nash equilibrium will be one where E is the same no matter what the opponent does. So now let's go about solving this. Let's step back and figure out what our goal is. Our goal here is trying to pick P1, P2, and P3 such that our expected damage is the same no matter what action the defender takes. So the way we're going to go about solving this is we're going to list 4 equations, and each equation is going to tell us something about the system. These equations are going to represent the concepts. The first equation says, what if the opponent always defends back? Well, if the opponent is always holding back no matter what happens? Well, recall that P1 is the probability that Wolf is going in the back direction. So in the case that the opponent is always defending back, then P1 percentage of the time, Wolf will deal no damage because he and the opponent both picked back, and so that was a throw break. Now, P2 percentage of the time, Wolf is going to deal 50 damage. Why? Because P2 is the probability that Wolf picked neutral, and since we're assuming in this equation here, since we're assuming in this equation here that the opponent is always defending back, then in this case, if Wolf picked neutral, P2% of the time, he would always deal 50 damage. Similarly, P3 percentage of the time, Wolf will deal 70 damage because the opponent is defending back, Wolf is attacking in the toward direction, so would deal 70 damage. The final expected damage of all these 3 cases would be E. Now, what does the second equation say? The second equation considers the case in which the opponent is always defending in the neutral position. Well, in this case, P1% of the time, Wolf will deal 65 damage. Because Wolf is going back, the opponent is defending neutral, so he would deal 65. P2% of the time, it would result in a throw break because Wolf and his opponent are both picking neutral, dealing no damage. And then P3% of the time, Wolf would deal 70 damage because he picks toward, his opponent picks neutral, and so he deals 70 damage. And on average, it would be E here. Now, why is E the same in both cases? E is the same in equation 1 and in equation 2 because we're trying to find a strategy that is independent of what the defender does. So we need to make sure that we get the same average damage no matter if he always holds back or always holds neutral. The third equation is similar to the first 2. In this case, we're assuming that the opponent is always defending in the toward direction. P1% of the time, Wolf will deal 65 damage because he picked back. P2, which corresponds to the percentage of the time that he picks neutral, P2% of the time he'll deal 50 damage. And finally, P3% of the time, which is when he's picking in the toward direction, then he would deal no damage because we've got a throw break, again dealing E damage on average. The fourth equation just tells us that our 3 probabilities must sum to 1. There's no other choice for Wolf to do. You could, in principle, say Wolf could choose to take no action, but we're not going to consider that case here. So we're considering 3 possible actions, P1, P2, and P3, and they must sum to 1, or 100% of the time. So if you go through this, you should get the following results. Excuse me, I'm going to go back and we'll edit this. So I encourage you at this point to pause the video and see if you can work out what P1, P2, and P3 are, as well as E. We have how many equations do we have? We have 4 equations. How many unknowns do we have? We have 4 unknowns. So you should be able to solve for every equation and every unknown. Now, if you go through the math, you should get these results. P1 comes out to about 31% of the time, which is how often wolf should go in the back direction. P2, 40% of the time, is how often he should go in the neutral direction. P3, 29% of the time, how often he should go in the toward direction. And finally, E, 40.27, which would be the average damage that wolf would get if both players are using the Nash equilibrium. Now, at first glance, this might seem wrong. It's telling us that wolf should do his least damaging throw most of the time. Isn't this wrong? Well, it's certainly unintuitive. Let's compare this with some of the other strategies we've discussed. There was the strategy we discussed of going toward all the time. Well, this seems good because you might say you're dealing 70 damage, but the opponent can just always break toward and escape every time, in which case, on average, you're dealing no damage. Well, clearly that's not very good. What about the other strategy we talked about, which was the 50-50 mix-up of going toward and back? Now, at first glance, this seems like a much more plausible strategy than the one that we've just computed, because you're doing the 2 most damaging throws. So let's work this out, assuming that the attacker and the defender pick randomly between those 2 choices. So when wolf picks toward, then half the time he's going to deal 70 damage. So half the time he'll deal 70 damage, half the time the throw will be broken, so on average he'll deal 35. Now, if wolf goes back, he'll land 65 damage half the time, and it will be broken half the time, which on average there would be 32.5. So the average between 32.5 and 35 is 33.75. Well, clearly that's much worse than 40.27, which is what wolf can expect to get if he follows the Nash equilibrium strategy. So unintuitive as that is, going neutral most of the time is actually going to net you more damage than picking a 50-50 mix-up between the 2 most damaging throws. The nice thing about this Nash equilibrium strategy is that it doesn't matter if your opponent is the world champion or even a computer programmed to play perfectly. Your opponent cannot stop you from achieving this damage on average. Now, of course, this assumes that you're really picking truly randomly. If you try to, say, cycle around and always pick toward, then pick back, then pick neutral twice or something like that, your opponent can pick up on what you're doing. So you really have to act in a truly random fashion. Now, is this possible? In theory, some would say no, that your brain can't pick things perfectly randomly, but this is still good to know as a case study of what mathematically our best average damage is. So now that we've gone over the Nash equilibrium for the attacker, let's go over the Nash equilibrium strategy for the defender. As before, we're going to set up a system of equations and unknowns and solve for them. So recall from our matrix that we had before, I'll go back and show it. Our matrix showed that whereas for the attacker we had 3 probabilities, P1, P2, and P3, that represented back, neutral, and toward, for the attacker. For the defender, we've got 3 probabilities, Q1, Q2, and Q3, that represent back, neutral, and toward. So what we want for the defender is we want the same expected damage regardless of the attacker's strategy. Now, we know that because this is a zero-sum game, the expected damage should be the same that we computed for the attacker, but let's not take that for granted right now, and let's compute it out and see what we get. So for the defender, we're going to want to take a set of strategies or probabilities for Q1, Q2, and Q3 such that we're going to minimize the damage that we take no matter what the attacker does. So as before, we're going to write 4 sets of equations, and let's look at them in some detail. So the first equation here, we're going to assume that the opponent, wolf in this case, is always attacking with a back throw. And Q1 percentage of the time we're going to escape back, Q2 percentage of the time we're going to escape neutral, and Q3 percentage of the time we're going to escape toward, with an average damage of E. So what does a set of equations say? Well, if we, in the world where Wolf is always attacking back, then Q1 percentage of the time we'll get escape the throw correctly, and we'll get take no damage. Q2 percentage of the time that we've escaped neutral, well, we take the back throw, so we eat 65 damage. And Q3 percentage of the time where we tried to escape toward, we also eat 65 damage, on average taking E. The second equation is what happens in the world where the wolf is always attacking with a neutral throw. Well, this equation says if we go back Q1 percentage of the time, we're going to eat 50 damage. If we go neutral, Q2 percentage of the time, we'll escape the throw and take no damage. And if we go toward, Q3 percentage of the time, we'll take 50 damage, again for E. And we want the E's to be the same because we want our probabilities Q1, Q2, and Q3 to be selected such that the damage we take is constant and minimized regardless of the attacker's strategy. And finally, we have our third equation. Well, what happens if Wolf always attacks in the front direction? Well, Q1 percentage of the time, we're going to take 70 damage. Same as Q2 percentage of the time. So if we escape back or neutral, we'll take 70 damage. But if we escape toward, Q3 percentage of the time, we'll take no damage. And finally, Q1, Q2, and Q3 must sum to 1. So again, I'll pause the video. I would suggest if you're interested in doing the math, pause the video here and see if you can work out from these 4 equations and 4 unknowns what the values of Q1, Q2, Q3, and E are. So if you work out the math for this, you should get the following answers. Q1 percentage of the time, Q1 equals 38%, so you should escape back 38% of the time. You should escape neutral 19.5% of the time, and you should escape toward 42.5% of the time. And the expected damage is 40.27, which, as we had predicted, because this is a zero-sum game, was the same expected damage that we got for the attacker's case. So let's look at some insights here. We've done the math for the attacker and for the defender. I've listed the results here in a table so that we can compare. What can we infer? So we've found that the attacker should go neutral the most often, and we've found that the defender should go towards the most often. Now, it might be intuitive that the defender has to defend the most damaging attack the most. 42.5% of the time, he should defend toward. And I think this feels right because you kind of want to block, try to escape the most damaging throw. But what might not be intuitive at all is that the attacker has to attack with neutral the most. And we went over that a couple slides ago, just giving an example of why attacking neutral 40% of the time was better than just mixing up back and toward 50-50 and having neutral 0% of the time. But at least I found it quite intuitive that the defender should block neutral, that the defender should block toward the most, but it was not intuitive that the attacker should attack with neutral the most. We found that the average damage is 40.26. So what does this table tell us? Well, this tells us the optimum strategies for the attacker and for the defender, assuming that the attacker and defender are themselves playing optimally. So you might ask, well, what if the opponent does something else? Well, if the opponent does something other than these probabilities, that means that you can exploit them. So, for example, if the attacker deviates, so as we went over the case before, if the attacker were to say, well, I'm just going to do back and toward, mix up those two and not do neutral, then as the defender, you could exploit that by blocking back and toward and not blocking neutral, and you would lower the expected damage you're taking down to 33 instead of 40.26. So these strategies are your average best case, assuming that your opponent is playing optimally. If your opponent deviates from these probabilities, then you could develop a counter strategy that would work to your advantage. Now, all of this is assuming that the defender has a lot of life. what happens if your life total is close to 0? Well, if the defender has less than, say, 50 life, your intuition might tell you that you can just do a 3-way pure mix-up, picking each direction equally, because each direction will kill the opponent. And your intuition would be absolutely correct here. In general, we don't want to score any damage that overkills. So if we do a 100-point combo on an opponent that has 20 life left, really we're only dealing 20 life and we don't get any brownie points for doing the extra damage. So generally, if the life total of the defender is below 70, we'd want to rewrite our equations taking into account the true damage that's dealt. For example, if the defender had only 65 life left, then in this case both the toward and back directions would count as doing 65. Even though the toward direction is supposed to do 70 damage, only 65 is really dealt. And neutral would still be 50. So in this case we'd have to rewrite our equations and calculate a new Nash equilibrium. Okay, so now let's look at the several ways that we can go into the standing net clutch. For raw, what we found is that, so Wolf can initiate the standing net clutch by doing the raw move, in which he will take some damage and then initiate a standing net clutch. He will eat the opponent's attack. So we know from our previous computation that the payoff of the standing net clutch is 40.26. So that means that it's profitable for Wolf to initiate raw if the attack that he's beating deals less than 40 damage. So if he's taking, say, a standing punch that deals, like 10 damage, then he would take that 10 damage and then deal 40, so that would be a profitable move. The other way that Wolf can go into the standing net clutch is via a heavy toe kick. Okay, so let's look at a couple of things here for the heavy toe kick, which is the other way that Wolf can initiate his standing net clutch. The heavy toe kick is a 16-frame mid that deals 17 damage and then continues into the standing net clutch stance. So we can compare this to Wolf's other 16-frame mid, which is his rolling back elbow, and this is a 16-frame mid that deals 39 damage. So we can ask the question, which is better, the heavy toe kick or the rolling back elbow? Maybe you're in a situation where you'd like to attack with a 16-frame mid, and you'd like which of these two options is the better one. Well, using the calculations that we've done before, we can now answer this question. The heavy toe kick into clutch will deal 17 damage for the heavy toe kick, and then go into the clutch stance, which we've computed as being worth 40.27 damage. From now on, I'm just going to call it 40 damage for simplicity. So we can say that on average, we're going to get roughly 57 expected damage. Now, this is variable damage. It ranges from 17 to 87. In the worst case, Wolf's opponent will escape immediately, and so Wolf will deal only 17 damage from the heavy toe kick. And in the best case, Wolf will deal his most damaging throw, which is the toward, for 70 damage, in which case he'd do 87. So the damage can range in between those two, but we know that at Nash equilibrium, Wolf can bank on average getting at least 40 damage. So the total expected damage would be 57, assuming that Wolf's opponent plays optimally. How does this compare to the rolling elbow? Well, that's a lot more damage than the rolling elbow. So you could say that the heavy toe kick is a more profitable attack. However, the rolling back elbow is 39 damage, and while that's less than 57 damage, it is guaranteed damage, which has its own advantages over variable damage. But it's definitely useful and good to know that we can compute the heavy toe kick move to be worth about 57 damage. So now let's go into variable versus guaranteed damage. A lot of people will say always go for guaranteed damage over variable damage. But is this really true? Well, is 57 variable damage better than 39 guaranteed damage? I think you could probably say yes. The 57 is quite a bit more than 39. But this brings up the interesting point. What about 57 variable damage? Is that better than 57 guaranteed damage? Right? This is an interesting thought experiment. You could say let's assume that Wolf had a mid attack that dealt that at 16 frames dealt 57 damage every time. Like, let's say that he could go from his toe kick into so back KG into K. Let's assume that that did 57 damage. It doesn't, but let's assume for the sake of argument that it did. Is that better than going from toe kick into the neck clutch, which could range from 17 to 87 damage? A lot of people would say no here, but is that really that obvious? Let's indulge in a thought experiment here. Let's assume that at the beginning of the round, you're given two choices. You could deal 110 damage, half-life, guaranteed to your opponent, or you could have a 50-50 shot at KOing your opponent instantly. Which would you pick? Well, it depends, right? Let's say that you're playing against the world VF champion. I can say that if it was me with this choice against the world champ, I would take the 50-50 chance of killing him every single time, no doubt. Because I know that even with a 50% life lead, I know that he's probably going to beat me. He is that good. So I'm much better off getting that guaranteed kill, or at least that shot at a guaranteed kill, than taking some damage. And I'm sure that if you asked the world champion what he would prefer that I would do, he would want me to take the guaranteed 110 damage because he knows that he'll beat me. In fact, to go on this point, I could say that against the world champion, if you gave me even more than half damage guaranteed versus the coin flip to kill him, I'd still take the coin flip. So we can modify this thought experiment and give me the choice between dealing 150 damage guaranteed or take a 50-50 to kill him. I would still take the 50-50 to kill him. This is called risk-seeking behavior. If I'm the worst player, I'm definitely going to take the riskier play that deals more damage. It's much better to swing for the fences if you're the worst player because you're going to lose a fair game. So the worst player would want to take those big risks. Now let's flip it around. Let's say that my opponent is worse than me, and I'm given the choice between getting to deal having a half-life advantage lead over him or a 50-50 shot at instantly killing him. Well, if he's worse, I would probably prefer to have the half-life lead over him. In fact, I would probably take even a worse deal. I would probably take a guaranteed 90 damage, which is less than half of his life, instead of a 50-50 chance at killing him. Because since I'm the better player, and I think I make better decisions than him over time, it's going to be much more consistent for me to take the guaranteed damage over the variable damage. This is known as risk-averse behavior. And this is a behavior you can see in poker, where if you look at high-stakes, no-limit Texas Hold'em, pros will often avoid going all-in versus an opponent that they think is worse than them, even if they have slightly better than 50-50 odds. A good player will avoid going all-in versus a bad player because the good player knows he's going to win over time. So take a heads-up poker. The good player is going to try to avoid going all-in unless he's got a really big advantage in his favor. Good players will avoid coin flip scenarios like ace-king versus a small pair, but bad players will try to go all in, even if the odds are not completely in their favor. So in the poker analogy, even if the worst player has a 40% chance to win all in and the good player has a 60% chance to win, the bad player is much more likely to take that bet and the good player likely to avoid it, because 40% is as good as it's going to get for the bad player. And the bad player knows that the longer he plays, the more chance he's going to lose, as there are more decisions to make in the long term, and the good player will win over time. So with that said, let's clarify something about variable versus guaranteed damage. If you can kill your opponent with guaranteed damage, you should always pick that. Killing your opponent is always the best move, so there's no reason to take variable damage if you guaranteed damage will kill your opponent right away. So in conclusion, let's look at the questions that we asked. We've answered our original questions, and they were, first of all, what's the best strategy to use? Well, the best strategy to use for the defender is a roughly even mix between toward and back, going neutral about 1/5 of the time. And the best strategy for the attacker is to go neutral 2/5 of the time and then mix toward and back the rest of the time with a slight bias toward back. How much damage can you expect to get? 40.27. Is it better than guaranteed damage, and under what conditions? Well, it's definitely better than Wolf's other 16-frame mid option on average. And then whether guaranteed versus variable damage is better, that depends on whether you're risk-seeking or risk-averse. But as a good rule of thumb, you can use the average damage from Nash Equilibrium to do a rough comparison of what they're worth. So now for those of you that would like to, interested in doing these kind of calculations on your own, here's an exercise. What is the expected damage for Wolf's standing leg clutch? Wolf's standing neck clutch is a similar stance as the standing neck clutch. In this case, Wolf can pick neutral for 55 damage. He can pick back for 65 damage, or he can pick toward for 60 damage. So see if you can follow along the example that was done before and calculate Wolf's probabilities, the defender's probabilities, and the expected damage in the standing leg clutch. Thanks for watching, and if you have any questions, please leave them in the comments. Thanks for watching.